Schönen guten Tag, meine Damen und Herren. Ich begrüße Sie zum heutigen Kolloquium. Thema aus dem Gebiet des Magnetismus haben wir heute bereit. Herr Yuriy Mokrousov wird uns vortragen. Er hat in Kiew studiert, seinen Master gemacht und ist dann an die Aachener Universität gewechselt, hat dort seinen Doktor gemacht. Die Reisezeit in der Postdoc hat ihn dann geführt auch an die Universität in Hamburg und dann später nach Berkeley, USA, Kalifornien. Dann zurückgekommen, ist Nachwuchsgruppenleiter an der RWTH in Aachen, zusammen wahrscheinlich mit dem Helmholtz-Zentrum in Jülich. Genau. Und seine Spezialität sind ab initio Berechnungen zu magnetischen Eigenschaften und er wird uns also heute vortragen. The talk will be on topological spintronics from Dirac monopoles to magnetic recording. Thank you very much.
Thank you very much. Thank you very much all for coming. Okay. And indeed today I'm going to talk about topological spintronics from Dirac monopoles to magnetic recording. As a motivation, let me start with the challenges which we currently face in technology. If we take a look at the basic parameters of the CPUs which we have in our computers or on our mobile devices, we will see that the main characteristics of these CPUs are actually stagnating in the last years. All of this is combined with the fact that actually the CPUs have very bad energetic efficiency and the fact that the IT is the branch of technology which is expanding constantly makes the CPU technology or IT technology as one of the major players in the consumption of energy, in particular in Germany or in Europe. On the other side, we witness an increase in the information which we would like to store and analyze. And this is also connected with the fact that we have more and more digital data, which is written on hard disks or DVDs or CDs, as compared to the data stored on the analog media. This revolution, a transition between analog to digital data, is largely due to the discovery or introduction of this magnetic hard disk. Magnetic hard disk is basically the most well-known, the most famous manifestation of spintronics in technology so far. And spintronics is the branch of technology which exploits not only the charge degree of freedom, but also the information which is encoded in the spin of our electron. On the other hand, one can make use of the currents of spin and transform information like this by using the spin currents. How this magnetic hard disk works, so actually what we have here are the magnetic domains which are ferromagnetic or collinear magnetization like particles. And what we can do is we can change their direction with the magnetic field, the process which is shown here. On the other hand, we can read the state of each of these bits by using, for example, the effect of giant magnetoresistance, first observed in '98, for which Albert Ferd and Peter Grunberg got the Nobel Prize. Here, the resistivity or the transport properties depend very strongly on the fact whether your reading head is collinear to your bit or parallel or in anti-parallel configuration. These challenges which I mentioned, they can be formulated in terms of these magnetic bits that we need and in terms of the currents which we have to generate and manipulate for transmission of information. So this basically concerns the generation, transport, manipulation, and detection of these objects. And in principle, what we want here is rather simple. It's very easy to formulate. What do we want are smaller bits, which we use for writing, which should be also robust with respect to different perturbations. And they should be able to operate at ultra-high frequencies. These are our requirements as well. We want to have a purely electrical control over these bits because the magnetic field, which we use currently, doesn't scale very much in size. And moreover, we want these things to be energetically cheap, not to consume a lot of energy. This is basically very simple. However, to achieve these design goals is not so simple, although there is a light at the end of the tunnel which is associated with a whole bunch of effects which can help us realize these ideas. You see the list of a number of those, and they're listed there not to scare you off, but basically to give you an impression of what kind of diverse physics participates here. What combines these phenomena in a common cup or in a common bunch is the spin-orbit interaction. And you know that the spin-orbit interaction is the interaction which couples the spin degree of freedom to the orbital degree of freedom of our electrons. The energy scale of spin-orbit interaction is of the order of 100 millielectron volt, and this is orders of magnitude smaller than the energy of chemical bonding, for example, or the processes which take place in the nuclei. These phenomena are based on spin-orbit interaction, and therefore the whole branch of spintronics, which is the next level of spintronic associated with this phenomena, is called spin-orbitronics. On such an energy scale, what becomes extremely important is the realistic simulations of complex materials which have to contribute to materials design and to the functionality design. And technically, this is where I work and where my group contributes. However, I will not lie to you, and I cannot tell you that these challenges we face in technology are the main motivational points for us. What is important, or what we find fascinating, is that many of these effects, which you again see listed here, connected to spin-orbit interaction, can be glued into a single family, and there can be connection established between all of them using the modern concepts of topology, which are also known to participate or have a profound role, for example, in such branches of physics as quantum field theory, molecular physics, and nuclear physics. What is fascinating here is that we can relate all of these effects into a single family, not only quantitatively, but actually we can provide down-to-earth expressions which allow us to compute this phenomena in most complex materials with amazing accuracy, which is important for material applications. How does it work out? I, of course, cannot tell you about everything, but I choose a set of selected examples, which includes Dzyaloshinskii-Moriya interaction, spin-orbit torque, the topological Hall effect, Skyrmions, and I will start probably with the Hall effects, because these are the most fundamental, historically first, and actually the most simple to understand effects. All right, so what is topology? And this thing is maybe known to many of you. Topology is an abstract branch of mathematics which deals with the general properties of geometrical objects. What is so interesting in topology is that topology has this notion of a smooth transformation between two objects. So we can take, for example, this coffee cup, and we can apply a certain smooth transformation, and we end up with a two-dimensional torus. Okay. Why do we need the smooth transformations? Is because, in principle, ideally, we are after what we call the topological properties. And these topological properties are robust versus such smooth transformations. For example, the ability to play soccer is a topological property of this ball, because we can do some horrible things to it, and at the end we can more or less still, play a game of soccer. What is important for topology, or what makes up for topology, is the local geometry from which these objects are built up. This is in exactly the same way that if we look at a certain planet, it looks like a nice sphere. However, if we look in more detail, you see that it's actually not very smooth and consists of these sort of craters. What is important is that it is the local geometry which determines the dynamics of a quantum system which lives on a certain object, on a certain space of parameters. A very simple example here would be, for example, the dynamics of a ball on a cup. So a cup has a certain curvature, so to say, which determines the local geometry of the cup, and the trajectory of this ball, if we push it on this cup, depends then purely on the geometry of this object. Okay, let's switch a little bit to more serious quantum mechanical terms, and let's imagine that we have a certain particle or a certain field which lives on a certain object. Let's say it is a chip. We say that our particle is given by this field U. Then what actually determines the geometry of this chip from the viewpoint of a particle is intuitively clear. It has to somehow relate the gradients of the change of this field across two independent dimensions on this chip. It is a rather intuitive definition. In physics, this quantity is known as the Berry curvature, and it characterizes how the chip is glued together. And it was actually Sir Michael Berry who realized for the first time the importance of this Berry curvature for the local dynamics of our quantum systems which live on such geometrical objects, not only chips, but also any abstract kind of object. Okay, so how can we apply this seemingly abstract thing to the solid state physics? And let's try. So in solid state physics, we have an array of atoms which are arranged in a regular lattice, and we're interested in magnets. And primarily, I'm interested at the moment in ferromagnets. So this means that all these spin moments on the atoms are aligned collinearly to each other. This is what we call a ferromagnet. The way to characterize the states in such a solids, this is basically fundamental solid state physics, is by the band, which is analogon of an energy state in chemical physics, but also by this reciprocal Bloch vector K, which is the reciprocal vector to our real space lattice. So at the end, the characterization of the electrons which live in this infinite system looks like this. We have certain bands which can be numbered, and these bands live in the reciprocal space. Why do we need the reciprocal space? This is because everything is periodic in the reciprocal space, and we can actually deal only with the unit cell here, which is inverse to the real space unit cell. You see that the energy of our electrons is actually periodic. This allows us to do a trick, and we can glue together the opposite parts of this unit cell in the reciprocal space, and what we end up is with the notion that our electrons live on this two-dimensional torus, which we can, let's say, embed in 3 dimensions and look at it like this. So this torus is our chip and field as far as the Bloch electron is concerned. What is so interesting about it? And it is actually very interesting that the first application of these abstract things was found in one of the oldest effects in the magnetism. This is the Hall effect. The ordinary Hall effect, many of you know, was discovered in 1879 by Edwin Hall, where he took a piece of metal, he applied an electric field to it, so he had some current. After that, he applied a magnetic field, and what he observed is the formation of this transverse Hall current. The formation of this current is due to the Lorentz force, which actually acts on propagating electrons, as you know. It is a force which does not depend on the spin of our particle. Only 1 year after this discovery, Edwin Hall discovered the Anomalous Hall effect, and in the Anomalous Hall effect, he realized that if he uses elemental ferromagnets, which are known to most of you, such as iron, nickel, or cobalt, he doesn't need any external field to produce this Hall effect, and actually the effect which he gets is like order of magnitude larger he gets in the ordinary Hall effect. It took years of research and understanding actually to summarize that the anomalous Hall effect, which I denote as AHE, arises in samples with non-zero macroscopic magnetization and due to spin-orbit interaction in these samples. Let's try to understand the anomalous Hall effect from the viewpoint of geometry. Let's remember now the curvature, the expression for the curvature of our electrons, which live in this reciprocal space. And here we have to substitute the x and y in a ferromagnet with spin-orbit interaction with these components of the reciprocal vector. You can check it actually by numerical calculations, but also by symmetry arguments to see that this quantity is non-zero in such a situation. Now, intuitively, what you would think the non-trivial curvature would lead to. It would lead to a coupled dynamics into orthogonal directions. What I mean here is that if we start a motion of our electron along certain k in our reciprocal space, the non-trivial curvature will couple these dynamics to the orthogonal direction. So we induce motion in the transverse channel. And this exactly explains the anomalous Hall effect on basically hand-waving arguments. Surprisingly, the anomalous Hall effect was the first door through which the concepts of geometry or topology entered the world of spintronics. This simple trick, which I did with the curvature, can be generalized actually to rather abstract situations. This means that if we have some abstract parameter spaces in which our system lives, then if we have a non-zero curvature, we can always expect some sort of coupled dynamics in 2 dimensions. And I'm going to use this trick once more at the end of my talk. It took 50 years of research to boil down this simple picture to the expressions which can be expressed in concrete terms. I give you here an expression for the velocity of the electrons, in real space, and it has a term which is the group velocity. This is the derivative of the energy with respect to the k vector, and the appearance of this geometric contribution to the velocity of our electrons, which is transverse to the applied electric field and purely due to the presence of this non-zero curvature. To obtain the Hall conductance, we can integrate this formula over the whole set of occupied states to come up with this famous formula for the Hall conductance, which tells us that it is nothing else but the flux of this Berry curvature through the whole torus of occupied states. And what is very surprising here is that this flux, and this we will see once more for Skyrmions, is quantized in insulators. And here I could take off and continue my lecture about topological insulators, which would be one option. However, I decide to stick to metals, and motivated by the fact that actually the physics in metals is rather complicated, not only from fundamental point of view, but also from computational point of view. Let's take a look at typical electronic structure. So this is the band structure of HCP cobalt. It consists of a huge amount of these electronic bands in the reciprocal space. What is particularly important that around the Fermi energy here we have a rather complicated situation. This complicated situation results in the fact that we have to use advanced computational techniques, and for our purposes we actually use the density functional theory, which I denote further on as the DFT. The topological or geometrical origin of all sorts of Hall effects, for example, spin Hall effect and anomalous Hall effect, has been studied from the density functional theory for 1 decade with actually great success. And one of the interesting points here that once we open the door to topology to enter our down-to-earth solid-state physics, then we immediately get the quirks which are typical for topology. For example, we get the Dirac monopoles in reciprocal space as the main sources of this curvature of the anomalous Hall effect. And these Dirac monopoles are given by these band degeneracies which occur in our reciprocal space. And they can only occur not only at a certain point, but also along these kind of lines, which we actually call the hot loops. What is a rather general observation is that the Berry curvature part of the anomalous Hall effect, or of all these effects I'm going to talk about, can be rather elegantly embedded into a whole notion of scattering independent contributions to the current. These are contributions which do not depend on the presence of disorder in our system. What we have shown in the past years that this scattering independent part of the Hall effect is actually dominant for what we call moderately dirty metals, and these are actually normal metals which we meet in our everyday life. What makes Hall effects, scattering independent Hall effects, so special is that they're actually very energy efficient. They don't cost us a lot of energy, and they provide a cheap source of generating these spin currents, which can transmit the information from object to object and which can be used to read out the state of our magnetic system. What is also important, and this is what we showed recently, is that the scattering independent picture of the Hall effects is not true only for the static electric fields, but it's also true for the high frequency electric fields, and this is a direct door for the high frequency terahertz spintronics. The next complex object which I'm going to consider, and where I'm trying to apply the concepts of geometry or topology, is the case of chiral magnetic skyrmions. What is a skyrmion? So, to some of you, skyrmion is maybe known as a soliton-like solution for baryons in the nonlinear sigma model, which was suggested by Tony Skyrmy in the 60s. What is fascinating for us, people working in applied magnetism, is that this kind of soliton solutions has been observed experimentally in magnetic systems, where by soliton solution I assume this kind of isolated variation of the magnetization of our ferromagnet. This kind of structures has been observed in different two-dimensional, three-dimensional systems, metals, and insulators, and you can have isolated skyrmions as depicted here, or you can even have the lattices of skyrmions, like solid-state lattices with a certain lattice constant. What makes skyrmions so important or interesting is that they are actually envisaged as the new sort of particles or magnetic bits for spintronics. Why is that possible? It is possible because they actually have a lot of fascinating properties. You need very low currents to move them around, so you spend very little energy. They have very high stability. It is very difficult to destroy them. They have suppressed scattering and defects, and in addition to that, you have a whole bunch of skyrmion-specific transport effects. And many things here are actually believed to do with the non-trivial topology or geometry of our skyrmions. So let me try to explain to you how does it work out and where can we actually squeeze in the topology in here. Let's consider the case of classical skyrmions, and these are the skyrmions which were observed in these B20 kind of 3D compounds, of which the most important representative historically also is the manganese silicide. So it looks roughly like this. It is a lattice of gigantic skyrmions of the order of 100 nanometer in size. You see that magnetization in each of the skyrmions somehow rotates in a non-trivial way, and we will understand a little bit better what it means. But for us, people which worked with Hall effects, this is a very complex situation because we are used to ferromagnets. These are simple guys, so they just have magnetization straight out of the plane. So what do we do here actually? We try to simplify the problem. We consider a process of an electron which propagates through such a medium, but very slowly, and in addition we assume that the magnetization changes very slowly in the vicinity of such an electron. As a result of a propagation of an electron in such a way, we can always assume that an electron is locally in the ferromagnetic surrounding. So we can apply computationally all the things that we have acquired by studying the Hall effects. However, the equations for such an called adiabatic motion of electron has to be worked out, and it can be done, and the equation for the motion actually looks like this. It is a very simple equation, and it looks in a very similar way to that we had for anomalous Hall effect in ferromagnets. It has a group velocity term, epsilon is the energy of our electrons, and it has a geometrical term which is related to this omega, which is the curvature of our space. One, however, has to take into account that the space now is more complicated. It is not only the reciprocal space, given here by the K, which takes place or plays a role for the dynamics of these electrons, but also the position within the electron, which I denote as R. This leads to the observation that our Berry curvature is actually a more complicated object. So in addition to this K-space part, due to the K dependence of our electrons, we have two additional parts. One of them is the real space Berry curvature, omega R. This is due to dependence of my wave function on the position in the skyrmion. And there is also a mixed part due to the mixed dependence on the K and on the position in the skyrmion. Basically, what you can do in a simple hand-waving way, looking at these dynamics, is what I call a skyrmionic cup. So we have an electron which has a certain trajectory on this kind of cup, and you can say that the skyrmion lies in the plane of this cup, while the reciprocal space is orthogonal to it. So what we are looking after, or what we can calculate using this equation, is the trajectory of our electron, which is controlled by this curvature. How valid is actually this nice, seemingly nice picture for skyrmions, and what can we extract from it? Can we extract from it something which is useful, which we can actually compare to the realistic experiments? Let me start with this real space Berry curvature. Let's consider a process of a propagation of an electron through such a complicated magnetically media. Everywhere the spin of electron is aligned with the local magnetization, and if we look at the dynamics, we will see that the wave function of this electron will acquire a complex phase as it propagates through the skyrmion. The situation here is very similar to a problem of spin 1/2 in magnetic field. The magnetic field here is generated by this Dirac monopole, which I mentioned, only now this Dirac monopole lives not in reciprocal space, but in the real space. The magnetic field which it generates is exactly gives us this real space Berry curvature. Now, in the case of this Dirac monopole, if we calculate the flux of the magnetic field through the sphere, we will see that it is a quantized quantity. It is the charge of our monopole. And exactly the same is true for the flux of this real space Berry curvature if we integrate it over the unit cell of this skyrmion. It is a quantized number. It is called the winding number. And it presents a topological property of our structure. This means that if we deform our skyrmion somehow in a smooth way, this charge will not change. And this is actually very important because this charge, the analytical expressions for which can be derived based only on the real space distribution of our magnetization, participates in all kinds of equations which govern the dynamics of our monopoles. If we look back at the equations which govern the dynamics on this skyrmionic cup, we will see that the role of this real space Berry curvature is actually to produce a Lorentz force on propagating electrons, but which is opposite for electrons of spin up and for electrons of spin down. This is different from the ordinary Hall effect, where the Lorentz force is spin independent. Now, we can try to estimate the magnitude of this real space Berry curvature, or this emergent field, as it is called. And we can do it, for example, for manganese silicide to obtain the order of 10 Tesla, which is actually rather gigantic. The funny thing is that by reducing the size of the skyrmions, you can acquire completely atomic-like gigantic values of these emergent fields. This means that these are important players in determining the electron dynamics of electrons which propagate through such skyrmions. In particular, this kind of emergent field and the Lorentz force which it exerts results in the so-called topological Hall effect, what I denote as THE. This topological Hall effect is a primary manifestation of skyrmionic topology, if that was true, actually, if it could be possible to observe it. And it could be a main tool to detect the presence of skyrmions, because it would be specific only to the skyrmion distribution of the magnetization. To test out these ansatz, or these ideas, we teamed up with a group of Christian Fleiderer, who performed these very nice measurements on manganese iron silicide alloys. What they did is they actually took manganese silicide and then they varied iron concentration. They measured the phase diagram of these materials as a function of temperature and as a function of magnetic field. And here what you see with the red, this little pocket, this is the pocket in the phase diagram where the skyrmion lattice actually emerges. In parallel with the phase diagram measurements, they also did the transverse Hall conductance measurements. And if you take a look at them carefully, you will see that in the high field part of your phase diagram, where you have ferromagnetic systems, you can measure the anomalous Hall effect, as we discussed in the beginning. However, when you are in this pocket where the skyrmions appear, there is a characteristic dip in your Hall conductance. And in principle, this is what we call the topological Hall effect. It can be measured. However, the question remained, how much of a geometry is remaining in this number? And this was the task which we set out to resolve. We asked our experimental colleagues to summarize their data on the anomalous Hall effect and topological Hall effect as a function of concentration in these alloys. And here you see this data, and this is where we step in. We calculate the electronic structure of these alloys, and for expert, I will just tell you that we tuned the spin moment of manganese to fit the experimental data, and we treated the effect of alloying, which is a rather non-trivial thing, within the virtual crystal approximation. And to compute the transport properties, we used the K-space Berry curvature approach to the anomalous Hall effect, and we used the Boltzmann theory to estimate the topological Hall effect. And here I plot one-to-one the experimental and theoretical data, and I state that we actually see an excellent or very good agreement between these two sets of data. What does it tell us? The first statement is that this geometrical viewpoint, which I so nicely, I hope, introduced, actually works out for skyrmions. The second message is that the way geometry works, it works in terms which we can actually access from the density functional theory in the most complicated compounds. These are very important messages for us. We did the same analysis in similar systems, and in particular we reached the same conclusions for manganese-rich phase of manganese iron germanium alloys. Okay, so let me now move on to the effect of Dzyaloshinskii-Moriya interaction, which is a very important interaction among the spins in our magnetic system. Why is it so important? I'll try to explain. The Dzyaloshinskii-Moriya interaction leads to the formation of various magnetic chiral structures at surfaces. You can have chiral spin spiral states, or you can have chiral domain walls, as well as the chiral skyrmions are appearing as a result of this Dzyaloshinskii-Moriya interaction in many cases. What does it mean? What is the chirality? What's the role of chirality here? If we take a look at these two spin configurations of our atoms, let's say, their energy will be degenerate. However, if we include the effect of spin-orbit interaction and we break the inversion symmetry, the Dzyaloshinskii-Moriya interaction, which now steps in, will favor one sort of state over the other. So this basically, in simple terms, it favors one chirality over the other. This interaction was discovered back in the 1950s by Dzyaloshinskii and Moriya, thus we have this very complicated name of this interaction. And speaking in terms of the spin spiral solutions of our magnetization, the Dzyaloshinskii-Moriya interaction makes an energetic difference between right propagating spin spirals and left propagating spin spirals, which is the handedness, which is the chirality of our spin spirals. Therefore, the Dzyaloshinskii-Moriya interaction actually leads to the fact that we can have some stable chiral solutions at surfaces which exist in time. And for example, you can see here an iron chain on an iridium substrate where such a stable spin spiral solution could be observed with the means of scanning tunneling microscopy, as we did in collaboration with the group of Roland Wiesendanger. From the viewpoint of hydrodynamics, actually, the Dzyaloshinskii-Moriya interaction would prefer a certain type of this whirlpool objects, which you sometimes see at the surface of water. In terms of skyrmions, the Dzyaloshinskii-Moriya interaction prefers a certain type of skyrmions. So here you see two different types of skyrmions which differ by their chirality. What it means is that if we start from center of this skyrmion and we go to the end of it, the magnetization will rotate in one way. And if we go here, we do the same operation, the magnetization will rotate in the opposite way. This means opposite chirality. Why is it so important? Why is the chirality actually so important? And this is because the chirality controls the way that our chiral subjects, our chiral objects, respond to external perturbations, such as electric fields or magnetic fields. Another thing which is important is that the magnitude of Dzyaloshinskii-Moriya interaction is able to tune the size or the diameter of these chiral objects. The larger your Dzyaloshinskii-Moriya interaction is, the faster your magnetization wants to chiral. So the smaller the radius of the chiral structures that you get. Okay, this is all very nice, but how can we understand this phenomenon, this important effect, from the viewpoint of the geometry or topology? And what we actually do, and this is a trick which is rather common to energetical quantities in the geometrical theory, we take a ferromagnetic system and we induce a certain magnetic perturbation on it. A spin spiral, a skyrmion, whatever you want. What you do now is you take those equations which we had for the particles propagating in the skyrmion to calculate the change in the energy. And the constant of proportionality is exactly the Dzyaloshinskii-Moriya interaction. If we do this, we end up with a rather rigorous and rather universal expression for the Dzyaloshinskii-Moriya interaction, which has two parts, and one of them is the one which comes purely from the Berry curvature part, and the other one is the local part. These two parts I'll try to clarify to you in the next slide. These are not just qualitative things. These are actually concrete expressions which can be formulated in terms of the wave functions of your electrons in rather complicated materials, metals, insulators, and so on and so forth. And of course, we were very eager to test whether these equations work out, because the way we obtain them is rather beautiful, actually. We compared the calculated value of Dzyaloshinskii-Moriya interaction in manganese silicide, and we obtained the value which agreed very well to experiments. The beauty of these expressions also is that we can study the DMI in systems of various size and various structural and chemical complexity. However, for us, the final test of the validity of this geometrical viewpoint at this important magnetic interaction was the study of the DMI in this manganese iron germanium family of alloys. What you see here is the behavior of the Dzyaloshinskii-Moriya interaction with respect to the concentration of iron in this family of alloys. It behaves rather nice, okay, but what happens here is this characteristic point where the DMI turns to 0. And basically, physically speaking, this means that if we were having skyrmions in this system, they wouldn't like to form, because there is no point in forming at this critical concentration of 80%, since the chirality is actually not defined. There is no energy gain in chiraling, right? And surprisingly, or actually astonishingly to us, at exactly the same concentration of 80% in the very same family of alloys, the group of Takuro observed the very same phenomenon. Actually, the absence of the skyrmion formation at exactly this concentration and diverges of the radius of the skyrmions as one approaches this point where the DMI turns to 0. Moreover, also the sign of chirality is in agreement with experiments, and this was a rather nice test of rigidity of this concept as applied to DMI. We also did it for other systems, in particular for iron, cobalt, germanium alloys, where we also find a similar trend where DMI vanishes and the size of these chiral textures actually blows up. Okay, so by now, what do we have? We have Hall effects. Okay, that's nice. We can generate spin currents. They're energetically efficient, and we can transport information using them. Then we have the skyrmions, which serve as some sort of magnetic bits, which we can use for spintronics because they're small, they're very robust, and so on and so forth. However, what we are missing so far is the tool to switch the magnetization electrically. So to control the magnetization in our system without using the magnetic fields, only the electric fields. And this effect comes out also from our analysis of the Dzyaloshinskii-Moriya interaction. Let me explain this to you in more detail. Let's say we're looking at a large ferromagnetic cluster. So we have a lot of spins which are aligned ferromagnetically. Then if we look at the spin which is in the center of this cluster, it can ask around its neighbors, and they will tell him the way they would like to chiral or to form a certain chiral solution. This is the local part of this Dzyaloshinskii-Moriya which I showed you before. However, if I look at the edge of this sample, I will see that there is a gradient of potential between because the potential inside the cluster and outside of it is different. This results in the formation of electric field, and what is this electric field doing? It's not only generating the Hall effect at the boundary, but it is also interacting with the magnetization at the boundary. So what it does, it coherently twists the magnetization at the edge of our sample. What the spin sees is that suddenly there is from the sky coming this preference towards a certain chirality. And this preference does not disappear as we increase the size of our cluster. It remains, and this is exactly this Berry curvature part of the Dzyaloshinskii-Moriya interaction. So this part can be important, and it can compete actually with this local part of our DMI and lead to the formation of these non-trivial chiral textures, for example, skyrmions. The effect here is very similar if you try to look at it hydrodynamically again. If we take a glass and then we start rotating it very fast, then we can create certain whirlpools in the glass of water. And this is due to the effect of the friction of water with the surface of this glass, right? And magnetically speaking, this is exactly the effect which would allow us to influence the magnetization with electrical means. It is called the spin-orbit torque, and its effect on magnetization is exactly like this. We have a wind of electrons which interact with our magnetization and are able somehow to twist it and to change it. It is a very nice phenomenon which was observed rather recently within the past 5 years. And even here, we can apply our geometrical concepts and understand where it is coming from. For this purpose, we again have to write down this curvature which we had for the Anomalous Hall effect and for the skyrmions, but now we have to consider a different space. It is not the K space, or it is the real space. It is the space of our K vectors and of the magnetization direction. If you compute this quantity in systems with ferromagnetic magnetization, for example, spin-orbit interaction and broken inversion symmetry, you will see that it is non-zero. This means that by exerting a certain dynamics along the reciprocal vector direction, that's our current, we can actually change our magnetization. By now we're already clever, and we can say that the spin-orbit torque is arising due to this Dirac monopole-like energetic degeneracies, which is now happening not in reciprocal space only, but also in more complex space of the K and magnetization direction vector. This is a rather amazing theory, which also ends up in very concrete expressions which one can program and which one can test on rather complex materials. We did so in the past years to discover that this picture of spin-orbit torque is in a very good accord to experimental findings as well. As I said, the spin-orbit torque is actually a very fancy or phenomenon in which a lot of promise is currently held, because it was shown that in these kind of structures where we have magnetic overlayer on a non-magnetic substrate, if we apply a current in this direction, we can generate a whole current in this direction and thereby exert a torque on the magnetization, and this torque can be so large as to allow us to switch the magnetization of this ferromagnet. This was observed in 2011. Actually, this means that we can use only electrical means to enable this switching of the magnetization, and we could maybe realize even the magnetic recording schemes which are based on spin-orbit interaction, which are based on the spin-orbit torque, to replace the current magnetic recording techniques that we use. Spin-orbit torque would allow us for full electrical control of magnetization. It is a clear route towards miniaturization because we can make these samples extremely thin. It has enhanced efficiency because, again, it is based on the Hall effects. It works at high frequencies, and even amazingly, you can switch the magnetization in antiferromagnetic structures with this phenomenon. And antiferromagnetic structures are where the spins are aligned like this, and which are not accessible by regular means such as magnetic field. And this opens a whole lot of vistas for the field which is known as antiferromagnetic spintronics. This basically brings me to the end of my talk, and I would like to draw here again these three pillars of modern spin orbitronics with which the developments in this area are envisaged to be associated with. These are the Hall effects, which we can use for detection and for spin current generation. These are chiral robust textures, which we could use for storage of magnetization. And this is spin orbit torque, or electrical means which we can exert to influence this magnetization. I believe that this could actually lead to the new generation of devices and so on and so forth. However, what is amazing here is that I was able to describe to you all these effects in the same language by referring to the same terms. And our great motivation here is to extend this roadmap of topological effects or topological spintronics to other phenomena which might be of importance for spintronics as well. At this point, I would like to thank the members of our topological project at Forschungszentrum Jülich. These are people which worked in my group over several years. You see a lot of smiley faces, which is nice. And in my talk, you have seen a lot of results by our topological asset in the group of Higher Cinema here in Mainz, this Jacob Gales. And I cannot not thank all the collaborators that we had within the past 5 or 7 years. Here you see the map of these guys, not only in Germany or in Europe, but also in the United States, which was a very exciting opportunity to collaborate on a whole multitude of effects, which are primarily related to these Berry phases, Berry curvature effects, and not only that, to the things which diversify our understanding of modern spintronics. And for this, I would like to thank you also for listening as well.
Thank you for this fascinating insight into magnetic specialities. Are there questions? A lot of questions.
Well, one question about how computationally expensive the calculations are. Let's calculate this iron, silicon.
So there is a reason I showed the supercomputer here. Yeah. So to calculate BCC iron, maybe you can avoid the supercomputer because you can treat it with one atom in the unit cell. But if you want to do something more complicated, like manganese silicide, you need a supercomputer. So these are really intricate phenomena where the scale is actually very small, and you have to work hard to get reliable values.
How many CPU hours or weeks or months or years is that?
This depends on the problem, but let's say, to calculate topological Hall effect for manganese silicide, this would take you maybe a couple of days on 1024 cores, something like this. Yeah. But this is the simplest of the compounds which you can have. And that's what makes it even more fascinating, that we have these expressions which come from very abstract things, but they result in implementations which are able to capture these sensitive effects. That's what I was trying to underline.
Yeah. I have a question concerning the preconditions to get the Barry phases.
Yeah.
I mean, in the topological insulators, there is some band inversion.
Right.
You did not address that. Now the question, is this also possible for normal metals, like BCC metals? Because there were indications for tungsten and molybdenum that there is.
Yes. Also for gold, for example.
And also for gold in a new work from...
Right, Claudia Felser.
Can you comment on that? Where does it come from? I mean, is there a hidden band inversion in the background and we don't know it and we don't see it? Or is it...
There are a lot of hidden band inversions because due to the nature of your solid. So at some parts of the